Okay, in this short section, we're going to talk about the phenomena of drain-induced barrier lowering, conveniently called DIBL, and punch-through. So these are effects which are related to the channel length modulation and subthreshold conduction that we've already talked about. So let's take the punch-through first, actually. So here's our MOSFET structure: drain, source, and then our gate. Now, we're going to look at the effect of applying a large source drain potential and what it does to the injection of carriers and to the channel length itself. So when we talked about channel length modulation, we learned that the application of a large source drain voltage will actually pinch off the channel at a certain point, where the addition of the source drain voltage plus the gate voltage results in the density of the inverted electron channel dropping below threshold. So this pinch-off point, I should say, will move closer and closer to the source as the V drain source is increased. What we also have to look at are the contours of constant electric field, of constant electric voltage. And then we can translate those into the actual band diagram in a moment. So what we have to imagine is the superposition of the voltage coming from the gate to the vertical one coming from the gate and the lateral one coming from the sides. So as the lateral one coming from the sides is being increased, what's actually happening here is that the energy barrier or the voltage barrier for electrons to be injected into the channel is actually going to lower eventually as this depletion width moves sideways. So I'm drawing here the lines of constant voltage, but then remember that the band diagram is just the electron charge times that voltage. And so we can draw a band diagram versus X here that looks the same. So the conduction band barrier for electrons will take this same shape. So your source drain voltage is between these 2 points, and then your gate voltage is modulating this up and down as you change the gate voltage. So the thing is, what will happen at large enough source drain voltage, this energy barrier for injecting the electrons into the channel will start to be lowered. And it'll take a lower relative bias between the gate and the source in order to inject the carriers. So that means now that, that the amount of current flowing through the channel is going to be dependent on the source drain voltage because of the normal effects we've talked about, but then also we're going to start to lower that barrier. And that means we're going to get more current for the same applied voltage. So whereas before we had an ideal MOSFET curve that looked like this, now our current with this drain-induced barrier lowering and the occurrence of punch-through, where the depletion width from the drain actually reaches all the way through the channel, we'll get curves that look more non-ideal. And the punch-through really just means that the thickness of this barrier has gone to 0. If you no longer have a distinct distinction between the depletion widths from this, coming from the source and drain sides, if they meet somewhere in the middle of the channel, then you'll turn essentially the entire IV curve into sub-threshold conduction. So these three topics, sub-threshold conduction, drain-induced barrier lowering, and punch-through, are all interrelated, and they have to do with the superposition of the depletion widths and the voltages coming from all three of the gates of the MOSFET. So as transistors have gotten smaller and smaller, scaling down to the tens of nanometer sizes for the lengths of the channel, these effects have become really critical, and in fact, you can no longer design MOSFETs as sort of a one-dimensional structure. It really has to be considered as a three-dimensional structure in terms of predicting the performance characteristics and what dopings and physical sizes will be needed. So that is going to wrap up our short section on drain-induced barrier lowering, including the punch-through effects. And remember that this really relates back to what we've talked about in terms of sub-threshold conduction also.